Vectors. Okay, so maybe you are in a physics class, maybe it's an introductory physics class, maybe it's calculus based, maybe it's algebra based, who knows? And you're at this point, it's like vectors. What the heck is a vector? And I know that it can be very complicated. I mean, I've been there. I've done a lot of vectors, but I was at the point where I didn't know what a vector was either. It's very confusing. So I'm going to tell you everything that you need to know and nothing more. But there is a lot of stuff. Okay, so just bear with me. So this is a picture right here of the vector field due to an electric charge rod. I just thought it looked good, so I'd put it there. So let's start off with this. This is a dog. This is not a vector. But you know, I want to give you something to think about. Things that we got to think about what is and what is not a vector, right? And a dog is not a vector. Okay, then what else is not a vector? Well, you know, a lot of times in physics, you're going to measure stuff. You could measure time. So you use a clock. This is old clock I found. It's an IBM clock from the 50s. I think it's awesome. You could measure mass. And so this is a mass, but these are scaled masses that you put on a balance and you can use to determine mass. You could measure the electric current. Here's an old ammeter I found that measures current in milliamps. You could measure length, right? Don't use the inches part, use the centimeters part, but it's a value on the ruler that would tell you the length. So if I measure time, I could get some value like this. T equals 13.5 seconds. I just made up that number. If I measure the mass, I could get 55 grams. Current, 3.1 milliamps. Length, 9.4 centimeters. So all of these have just one value. It's just one thing. 13.5. Yes, it has a units. That's fine too. But it has just one piece of information. Okay. These are all examples of things we call scalars. If we want to know what a vector is, we have to first understand what a scalar is. So a scalar are these single pieces of information, and that's what we've looked at before. Color would be a scalar. I'm trying to think of another one. Your age is a scalar. Your grade in physics is a scalar. Okay. Now, you can have a scalar field. So this is another picture of my dog. This is an infrared picture. And so every point in this picture represents a different temperature. So let's say we flatten it out into 2 dimensions or even 3 dimensions if you use a spatial thing. Every point in there has one single value for the temperature. Okay, so even though the temperature is different at different places, every point has a scalar temperature value. So temperature is a scalar value. I just want to get that out there just because I wanted to use this picture. And that's really all. Okay, so let's talk about things that are not scalars. Let's consider the following situations. Suppose that you are a stick figure and you're standing on a number line. And why are there numbers there? I don't know. There are. Okay, and you're at the number 1 meter. And so someone gives you instructions and they say, move 2 meters. Okay, well, that seems pretty easy. Okay, and to make things even better, to kind of make it interesting, there's a flower right there. So you're at 1 meter and the flower is at 3 meters. So, oh, that's gonna be great. You're going to get to the flower. But at 0 meter is a fire. Okay, so if I move 2 meters in the positive direction, then I would get the flower. That's good. If I move 2 meters in the negative direction, something different happens. So you can see here that 2 meters doesn't tell you the whole thing. You have to say in which direction. 2 meters in the positive direction, 2 meters in the negative direction. So direction matters. And so this is an example of something that we would treat as a vector. Technically, this is a one-dimensional vector because you can move either in the positive x direction or the negative x direction, and those are different things. Of course, I could move in 2 dimensions. So here's a ball that starts at the origin, and I have, again, some axes. This is like the x and the y directions. I've just picked these out. And so the ball moves over here. How do we describe the motion of that ball? Well, it moved from the origin to there. And so it actually moved 5 meters in the x direction, because now it's at x equals 5. And it moved 2 meters in the y direction. So it moves plus 5 meters in the x direction, plus 2 meters in the y direction, and that's where it is. So this is an example of a 2-dimensional vector, right? Because I have 2 pieces of information. How much did it move in the x direction? How much did it move in the y direction? Okay, so why do we care about vectors? What kind of things can be vectors? We've seen what kind of things can be scalars. So what can be a vector? Here are the ones that you're going to encounter in the first semester of physics. Position, which we just saw, right? That was the position of the ball, had at least 2 dimensions. So it had an x and a y value. Displacement, that's the change in position. We're going to do an example of that. Velocity, so how fast is something moving? It doesn't just matter it matters which direction it's moving in too, right? It depends on which direction, how fast it's moving in the x direction, how fast it's moving in the y direction. So it's a vector. Acceleration also depends on direction, right? It's not just a single number. It has more than one number, so it's a vector. Force depends on which way you push things, also a vector. And there's many more. You'll do a lot more in the second semester of physics: the electric field, the magnetic field, the gravitational field. Okay. So how do we talk about vectors? How do we use vectors? How do we represent vectors? Well, how do we talk about scalars? You've already seen that. If I have a scalar variable, and let's say I want to call it temperature, I just use capital T. That'd be a good idea to use for temperature, T. Okay. But how do I know that T is a temperature and a scalar value rather than a vector value? What we like to do is to denote a vector variable in a little different way. We'd like to have the vector for position as the vector r. And there's a reason that we use r, but don't worry about it. And we denote that it's a vector because it has an arrow over it. So if it has an arrow over the letter, then we say that's a vector variable. And that way we know we treat it differently because it's a different kind of number. We have to do that. Okay. Now, in the older textbooks, they would use, that is bold R right there. They would put the vectors in bold, and that was probably a typo reason because it's easier to typeset bold, but you can't draw things in bold, right? So I hope you're not using a textbook that has bold vectors, but if you do, we just have to deal with what we have, right? So you move on. But you're probably not going to, when you write them on your paper, you're not going to write bold vectors because it's just a bad idea. Okay, so there's another way that we can deal with vectors. First thing we want to deal with vectors is a graphical representation. So here is the graphical representation of a vector A. You can tell it's a vector because there's an arrow over it. And so in this case, the beginning to the end of the arrow is the vector. And this is in 2 dimensions, but I'll show you one in 3 dimensions in a little bit. So that arrow represents our vector. Now, if you're dealing with the position vector, you could have the position vector be the actual distance of the arrow. But if we want to represent like 3 meters, I'm not going to draw a 3-meter arrow on my screen. So that's just a representation of a vector. It's not the actual vector. If I move the vector over here, it's still the same vector, right? Because it's still the same length and direction of that arrow. It's the length and the direction of that arrow that matters. Here's another vector, vector B. You can tell it's a vector because it has an arrow over it. You can tell it's a different vector because it's a different color. It's also in a different direction. Okay. Here's another vector, vector C. And what do we do about these vectors? Vector A and vector B are not the same because they don't have the same arrow. It doesn't matter where it's at. It just matters about that arrow. However, vector A and C are the same. They're the exact same length and direction of arrow, so they're equivalent vectors. So A is equal to the vector C. Okay, so like I said, you can have vectors in 3 dimensions. Here's a 3-dimensional vector. I made this in Python just so you can see it has an X, Y, and Z component. We don't like to draw those in paper because you can't draw 3-dimensional vectors very easily. However, there are situations, torque, magnetic field, magnetic forces, where you cannot do it in 2 dimensions. It has to be in 3 dimensions. We live in 3 dimensions. It's a 3-dimensional world. So, okay. How do you add vectors? So let's say that I have the following situation. I move 2 meters, and then I move 3 meters, and the question is, how far did you move? Well, let's just draw that out. So here's a displacement of 2 meters. I moved 2 meters to the right, and then I moved 3 meters to the right. So how far did I go? Well, I went 5 meters. That one's pretty easy, right? If I go 2 meters that way, and then 3 meters that way, I went 5 meters. Okay, let's do it again. Move 2 meters. Now move 3 meters. So I move 2 meters to the right. But what if I move 3 meters to the left? No one said which direction. They just said move, right? So in that case, I would end up moving a total distance of 1 meter to the left. But that's still not so bad, right? 2 to the right is like plus 2. 3 to the left is like minus 3. So 2 minus 3 is negative 1. So negative 1 would be my answer. I can do that one too. That's not too hard. Okay, let's do it again. Move 2 meters. I move 2 meters to the right. And then move 3 meters. I'm going to move 3 meters up. Well, how far did I go? Well, actually, we can figure this out, and I'll show you how. But I actually went 3.6 meters. So notice that the first case I had a distance of 5 meters. The second case I had a distance of negative 1 meter. And so this is a value in between those two. Okay. Here's another case. What if I move 2 meters to the right and then 3 meters at an angle? Well, that's going to be some other distance. It's actually going to be further than what I moved in the 2 meters left and 3 meters up, but it's some other distance. So the question is, how do we find these distances in these cases? Well, let's first consider what if you add more than one vector. So you'll notice in all of these cases, when I add vectors, the resultant vector is from the beginning of the first vector to the end of the second vector. And I put the vectors tip to tail, right? So the tip is the pointy part and the tail is the non-pointy part. So I start tail, tip, and then I do tail, tip. And then the resultant is from the tail of the first one to the tip of the last one. Okay, so I put this, I already said this. So I put one vector at the end of another, tip, tail to tip. The resultant is from the tail of the first tip to the tip of the last one. And so if I'm going to have 3 vectors, A, B, and C, and the resultant of that addition is going to be vector D. And it turns out that the order doesn't matter. So let's do this 3-vector addition. So here's vector A. Now I'm going to take vector B. Remember, I can move it and put it wherever I want. So I'm going to put the tail of B at the tip of A. And then I'm going to do the same thing. I'm going to put the tail of C at the tip of B. And then my resultant, the whole solution, the vector D, is going to be from the tail of A to the tip of C, and it looks like that. They don't perfectly line up just because I wanted to make sure we could see the arrows, but you could imagine that they actually would. And if these were distance vectors, then you can consider moving in these actual ways. And now the question is, well, then how far is D? And that's a much more complicated question, which we're going to answer. Okay, but I want to show you that it doesn't matter which order I do these in. I could go C and then A and then B, and it would look like this. So here you go C, and then I go A, and then I go B. But you see the vector D is the same in both cases. So it doesn't matter which order you add these up graphically, and in any case, it doesn't matter. You can add them up in any way you want. What about subtracting vectors? So one of the things that we look at in physics is this idea of the displacement vector, delta R. So if I have an object at position 1, I call it R1, and it moves over here to position 2, R2. What I want to know is how far it moved, and we call that delta R. So you could find this case going from the tip of vector 1 to the tip of vector 2. And it's actually subtraction, right? Anytime we have a change in, delta means change, it's final minus initial. So you can also do it by adding a negative vector. Okay, so let's take the vector R2. Now let's take negative of R1. If I take the negative of R1, it's the same thing as R1 except it's just flipped in direction. So here's negative R1. Now I'm adding this. I'm adding R2 plus negative R1. So I go from the tail of R2 to the tip of R1, and I get delta R, and you see that's the same exact vector. Okay, so we can subtract vectors. You can do it either way. You can just say from the tip to tip, or you can reverse the direction of one of them. It doesn't matter. But we don't normally do serious vector calculations graphically anyway. It's important to visualize it, but we don't normally do it that way. Okay, there's another thing that's not often covered in algebra-based physics courses, but it is covered in calculus-based physics courses, and it actually is super important, and it's a unit vector. So suppose I have this vector A, and I want to write it in a different way. I actually can write it like this. A times A hat. Okay, so A is just the scalar length of vector A, which we'll talk about in a little bit. And A hat is a unit vector in the direction of A. So a unit vector has a magnitude, a length of 1, and it has no units. So, but when I take that scalar and I multiply it by that unit vector, I get a vector. And so it's a way to kind of like break things up. And in this one, it doesn't make sense why you would do that. I can see why you wouldn't understand that. But there are some very special and important unit vectors I would like to introduce you to. And they are called x hat and y hat. So x hat is a vector in the x direction and it has a length of 1. So it doesn't, you can multiply it and it doesn't change your number because you're multiplying by 1. And y is a unit vector in the y direction. And then there's z too. Okay, so we can use this to do something super important. I can take a vector A and I can break this into two parts, right? Just like I did A plus B plus C is the vector D, I can go backwards. I can take a vector A and break it into the sum of two things. So I want to take this and break it into a vector in the x direction, which I'll call A sub x, the x component, and I have to make it a vector, so I have that x hat there. And then I have a y component, a y hat. So you can see here that these two vectors, ax, x hat plus ay, y hat, do add up to the vector a, right? So I start with a, the tail of ax, and then I add ay to the end of ax, and then I take the vector a from the tail of ax to the tip of ay, and it does work. Okay. And so in fact, we can write this out as a vector. A, the vector A, is ax, x hat plus ay, y hat. This is so super important that you wouldn't even believe, and you're going to see how useful this is. But then you may be saying, well, that's cool and everything, but how do I get these ax's and ay's? Well, here's an example. Suppose I have a vector that's 8 meters long and at an angle of 34 degrees. I can find the x and the y components because this is a right triangle. That's what's so great about using these Cartesian coordinates, x hat and y hat, is that they're always perpendicular. And since x hat and y hat are perpendicular, ax and ay are perpendicular, and so now I have a right triangle. If I have a right triangle, I can use right triangle trig. So if I take the sine of the angle, sine of 34, the sine is defined as the ratio of the opposite over the hypotenuse. So in this case, the opposite side is the y component, ay, and the hypotenuse is 8. So sine of 34 has to be ay over 8. I can solve this for ay by multiplying both sides by 8, and I get ay is 8 meters times the sine of 34 degrees. Make sure your calculator's in degrees mode, and I get 4.47 meters. Now that's my ay value. I can do the same thing by considering the cosine of 34. Cosine is defined as adjacent over hypotenuse. So in this case, the adjacent side is ax. So cosine of 34 is ax divided by 8. And then I can again solve for ax by multiplying both sides by 8. And I get 8 times, oops, that's a typo there. That should be cosine 34 equals 6.63 meters. And then I get the vector A, I can write it as the following numbers: 6.63 meters x hat plus 4.47 meters y hat. And yes, you have to have those units there, right? Vectors do have units. I mean, unless they don't, but most of them do, unless it's a unit vector. Okay. Now, you can have a negative component. Here's another vector A at some angle. But in this case, I have the x component I would write as ax is negative a cosine theta because it's going in the negative x direction. Remember, x hat is moving in the positive x direction. So if I want to represent that ax vector, I need a negative sign there. And that's the way I would do it. Ay would just be normal because it's already in the y direction. Now, some people may say, oh, but don't do that. Always measure your angles from the positive x-axis and things work. And they are right. If I measure this angle alpha from the positive x-axis, it's greater than 90 degrees. And if I take the cosine of something greater than 90, I get a negative number. So you could just use the angle alpha and say ax is a cosine alpha. I think it makes more sense just to say cosine of theta and then just make sure you're the human. Make sure it's negative if it should be negative. Make sure it's positive if it should be positive. But you also have to be careful because it's not always cosine for the x component. So here's another vector. The vector A is those are my x and y axis. I didn't draw them. But I've measured the angle theta from the negative y direction. So in this case, I would say ax is a sine theta, right? Because remember, I say sine theta, and that's going to be opposite over a hypotenuse. So in this case, the opposite side is the x component. It's ax. So it's ax over a. And if I solve that for ax, I get a sine theta. And it's positive because it's in the positive x direction. And then I would write the y component as negative a cosine theta. So be very careful. Don't just say cosine is x, sine is y. You got to look at your picture, right? We're really dealing with ratios of sides of triangles. So don't just write down some formula and just go with it. That's a bad idea. Okay, now for the magnitude of a vector, I would tell you about this. What if I know the components? What if I know ay and I know ax? How do I find the length of a, which we call the magnitude? So there's two ways to do this, right? I can write the vector a. If I put absolute value signs around a vector, that means magnitude. So that makes it into a scalar. Okay. I could also just write it as a without the arrow. So you will see both of those versions in both your class and in the textbook. But now I can use the Pythagorean theorem, right? I have a right triangle. So if I say a squared plus b squared is c squared, c is the magnitude of the vector. So I have ax squared plus ay squared, and then I want to find a, so I have to take the square root of that. So I'm just using the Pythagorean theorem to find that. And if I do that in this case, I get 3 squared plus 2.5 squared, and then I take the square root, and I get 3.91 meters. Positive. You'll never get a negative magnitude because you're squaring both things. They would be positive after that. Okay, why do we really care? It's really about adding vectors. And adding vectors graphically is not really easy. We need a better way. So we're going to add vectors using components. So here are two vectors, vector A and vector B, and I want to find the result of A plus B. Well, vector A, I can break into an x component and a y component. And vector B, I can break into an x component and a y component. And then since, remember, the order of adding vectors doesn't matter. X hat is a vector. Y hat is a vector. Okay, these are vectors, and I can change the order in which I add them. So if I do that, it actually looks like this, and you can see the cyan x vectors are in the same direction. Okay, or they could even be in completely opposite directions, but those are easy things to do, right? If I just take those components and add them together, and I have my x components. And the same thing for the y. I take my components and I add them together, and that's easy to do. And then I have two vectors that are perpendicular to each other. That's also not impossible to do. So neither of these vectors are in the x or y directions, and they're not perpendicular. But if I break them into components, I can add the components together. That's easy. And then if I have an x component and a y component, I can deal with that too. Okay, so in this case, let's call the vector c is the sum of a plus b. So the component of the vector c would just be ax plus bx. So if I find ax, the scalar value, it could be negative, okay, and bx could be negative, it depends, then I add those together and I get my x component of c. Same thing for y. ay plus by is cy. So then my total vector c is just going to be the sum of the x components, x hat, plus the sum of the y components, y hat. That's doable, okay. Now, I do think that we should take a break here and talk about styles, right? Because I don't know who you are, right? I don't know what book you're using. I don't know if you're using a book. I don't know what your instructor is using. I don't know. Maybe you're the instructor. I don't know. Maybe you're a robot. I don't know. Okay. So, but there are 3 common ways to represent these vectors with components. This is the way that probably is the most common, is to say the vector A is the x component times that vector x hat plus y component times the vector y hat plus z component, you could have a z component, times z hat. Now, some other books use, instead of x hat, y hat, and z hat, they do the same thing, but they use I hat, j hat, k hat, because they're like, hey, I don't want to do x hat. That's just not cool. I want to do I hat. I think I hat's cool. And if you think that's cool, I'm cool with that, okay? But just to realize it's the same thing. It's just a different notation. Finally, there's another notation that I like, and it looks like this. We don't even put the components. We just assume they're there. I put these angle brackets, and then I put an ordered pair, x component, y component, z component. And it's just assumed that there are unit vectors there. The nice thing about this is it takes less notation. You don't have to draw the hats. And this, if you're making vectors in a computer program like Python, it's much more like the way you would do it. So I like it that way. But again, these are all the same thing. Okay, let's do an example. Here are two forces acting on a block, and I want to find the net force. And so in this case, and it's done a lot of times like this, I have the magnitudes of the two forces, and then the directions drawn. So F1 is 4 newtons down. F2 is 3 newtons at this angle of 35 degrees like that. So the very first thing I need to do for this example to find the net force F1 plus F2 is to pick a direction for x hat and y hat. X hat and y hat are not real. So I am the human, I get to pick. Okay. And in this case, I'm going to pick x hat as horizontal, y hat as vertical. But you could do anything, right? It could be anywhere. So with that, I can now write my vectors in component notation. So let's start with F1. It's pretty easy. So F1, if we just look at it, okay, it's only going in the negative y direction. So it's not going in it's not pushing in the x direction at all. So its x component is just 0. You don't even have to put it, right? I have to put 0 x hat, but 0 x hat is just 0. I guess it'd be better to put 0 x hat. And then its whole thing is in, oh, I got those backwards. Okay, well, I'm not gonna stop. I'm too far in, okay? I called F1 down here in the bottom. Let's just switch. Let's say F1 is 3 and F2 is 4. Okay, sorry. And so it'd be negative 3 y hat. And it does have units newtons. Now, what about F2? Okay, so F2 has an x component and a y component, and I need to find those. So and I should have drawn these component arrows, but F2x, the x component, is the opposite side of that triangle, right? Because here I'm measuring that angle from the y-axis. I did that on purpose, okay? And it's in the negative x direction. So I need to take the negative sine of theta times F2 to get my F2x. And I need to take the cosine theta for my y component. And if I do that, I get negative 1.72 x hat plus 2.46 y hat, and I hope that's with the number 4. But I might have switched that up, but it's fine. Okay. Now I can find the net force in the x direction by just taking the x components and add them together. So the x component for F1 is 0. The x component for F2 is negative 1.72. I can add those together pretty easily, and I get negative 1.72 newtons. Now I need to do the same thing for the y direction. I have 2.46 is the y component of F2, and then minus 3 is the y component of F1. And so if I add those two together, I get minus negative 0.54 newtons. Again, there are units. And with that, I can get the total vector force F net is negative 1.72 x hat minus 0.54 y hat newtons. And that's the answer. Okay, now, a lot of times say, well, you got to find the magnitude and direction. Well, if your instructor says you have to do that, then you have to do that. But that is the answer. Okay, component notation is the vector. You may want the magnitude for something else, but this is the best form. Honestly, that's the best form. But let's do it anyway. Oh, and this is what it would look like. There's negative 1.72 in the x direction and negative 0.54 in the y direction. That's what that vector would look like. Okay, so what if I want to find the magnitude of F net and I want to find the angle, which in this case I'm calling alpha. So here's my vector, same thing as before. So I can find the magnitude of that by just using Pythagorean theorem. It's going to be negative 1.72 squared plus negative 1.54 squared, and I get 1.8 newtons. What if I want to find the angle alpha? So here's my picture right there. That's the same vector force, and that's the same angle. So I have my x and y components just like that, and I have a right triangle again. So if I know the values of my components, I can use the tangent, right? The tangent of alpha is defined as opposite over adjacent. So in this case, even though the triangle's flipped upside down, I don't really care. I'm just going to take the magnitude of fy, that's my opposite value, the magnitude of fx, divide those two, and that would be my tangent. And then I can take the inverse tangent of both sides to get my angle. So I get inverse tangent of fy over fx using just the positive values. Okay, if you use negative values, you're going to get a different angle. And you have to be careful with tangent because, you know, if you have negative f, if you have a negative y and a negative x, then those negatives cancel and you would think it's in the first quadrant. So just be careful about that. So in this case, I get 17.4 degrees, but I drew the angle, right, from below the y-axis. So that's, you have to describe that. If you want to get it from the positive x-axis, you just add 180 to that. Okay. What about scalar multiplication? You can indeed multiply a scalar and a vector value. And in fact, in the first semester of physics, you do this all the time. You say, what's the gravitational force? It's mass times g. G is the gravitational field. And g is the gravitational field with the value of 0 x component, negative 9.8 in the y direction, 0 in the z direction, and it has units of newtons per kilogram. And I'm using my angle bracket notation because I think that's cool. So I just want to multiply that by the mass to get the total force. So just a quick note, that's the gravitational field g. Some people call it the acceleration due to gravity, which I'm fine with. It's just not the best thing to do. And you will also see this a lot, g without the vector. Don't put g without the vector as 9.8. G is the magnitude of the gravitational field. So it would be a positive value, right? Because you're going to square all those components and add them together, then take the square root. So g is 9.8 newtons per kilogram. G vector is 0, negative 9.80. Okay, that's a different. So if I multiply mass times g, I just multiply each component by the mass. In general, if I have some scalar value s times some vector value a, then the x component would be s times ax, the y component would be s times ay, and the z component would be s times az. So you just multiply each component by that scalar value. And you can do that, and we do that again. You cannot multiply two vectors, okay? You can't say f times v, and they're both vectors. There are two vector operations. I'm not going to get into them today. The first is called the vector product or the cross product, and it's two ways to operate two vectors together in which you get a vector answer. Okay, and I'm not going to talk about that, just letting you know it exists. And there's a scalar product, also known as a dot product, where you operate two vectors together in some way and it returns a scalar value. So that one you definitely have to use in the first semester of physics. The cross product you use when you talk about torque, but you may not do that. In the second semester of physics, you pretty much have to use, when you talk about magnetic fields, you have to use the cross product. Sorry. Okay, vectors aren't negative. Okay, you can't, so here's a great example. Let's say I have these three forces acting on an object, and I want to find the net force. The net force would be this. F net is F1 plus F2 plus mg. Okay, it would not be minus mg. Okay, as a vector equation, it would be F1 plus F2 plus mg. Yes, g has a negative y component, and so if you wrote down the y values, it would have a negative. Okay, the component in the y direction is negative, but the vector itself is not negative. You can multiply a vector by -1. You can subtract vectors. Okay, but the vector itself is not negative. You don't say g is a negative vector because it could be negative in the y direction, positive in the x direction. Then what do you do? Okay. There's another very important vector called the zero vector. So what if these vectors all add, this is an equilibrium and the net force is 0? How would I write that? I would write it like this. F net, the vector F net is equal to the vector 0 newtons. Okay. And the zero vector looks like this. It's just 0 in the x direction, 0 in the y direction, 0 in the z direction. And that is important. Okay. There is a zero vector. You cannot do this. F net is 1.2 kilograms times 2.3 meters per second squared, because this is setting a vector on the left, F net, to a scalar on the right. That's not a vector. Okay, so you cannot do that. Okay, so that's one of the biggest mistakes I see students make is they have an equation and one side's a vector and one side's not. Two things, that equal sign means they are equal. And you can't have something with 3 pieces of information be equal to something with 1 piece of information. Okay, so just be very careful about that. Okay, so I'm going to end right there. That's enough vectors for you. You're not going to really fully grasp vectors until you practice. So get out there and practice. Do a lot of problems. And I hope that helps. I will talk to you later.